Hi, let's discuss Bellman-Ford algorithm. Bellman-Ford algorithm is used for finding single source shortest path. I already discussed one algorithm for finding single source shortest path, that is Dijkstra algorithm. If we already have one algorithm, then why we are using Bellman-Ford algorithm? If graph of negative weighted S, then Dijkstra algorithm doesn't work, whereas Bellman-Ford algorithm work. So the Bellman-Ford algorithm solves single source shortest path problem in which edge weight may be negative. The Bellman-Ford algorithm return Boolean value means either true or false, indicating whether or not there is a negative weight cycle that is reachable from the source. If there is negative weighted cycle, then no solution exists. If no negative weighted cycle, then it will return the single source shortest path and their weight. So Bellman-Ford algorithm work if negative weights are present but no negative weight cycle. If negative weight cycle present, then it will not show the shortest path. So the algorithm relaxes edges, progressively decreasing an estimate b dot d means distance on the weight of the shortest path from source to each vertex v belongs to v. This v for vertex, this v for all vertex in the graph until it achieves the actual shortest path weight. So it will return true if and only if the graph contains no negative weight cycle that is reachable from the source. If negative weight cycle present that is reachable from the source, then it will not show the shortest path. Let's discuss the algorithm. Bellman-Ford weighted graph is given, graph, weight and source is given. First, initialize single source GS. So in the graph, S distance will be 0, rest all other vertex distance will be infinitive. I already discussed initialize single source in greedy technique. Next, for I equals to 1 to G dot B minus 1, for each edge UV belongs to graph edge, relax UVW. So for I equals to 1 till number of vertices minus 1, will relax each edges. Means every edges we can relax up to number of vertices minus 1. Suppose there are n vertices, then n minus 1 time we can relax every edges. So after this, again for each edge UV belongs to graph edge, if b dot d greater than u dot d plus w uv, then return false. Means after doing number of vertices minus 1 time relaxation, if again it is relaxing, this step is for relaxation. Again the distance is updating, then return false, else return true. So this initialize single source run order of v time. Then this for loop, it will run number of vertices minus 1 time. Then this for loop will run for every edges. So order of e. Again this for loop will run order of e time, as it will run for every edges. So total running time will be order of v e. Number of vertices multiplication number of edges. Let's discuss one example. Bellman-Ford algorithm return true for this example. So first step, initialize single source GS. So S distance is 0, rest all other vertices distance is infinitive. Then for I equals to 1 to number of vertices minus 1. How many vertices are there? 5 vertices. So 5 minus 1, it will be 4. Then for each edge UV belongs to G dot E, relax UVW. So each edge we can relax maximum 4 times. Now t and y are reachable from source. Previously t cost was infinite, now it will be 0 plus 6. Infinite is greater than 0 plus 6. So after relaxation t value will be 6. Then y cost was infinite, now it will be 0 plus 7. Infinite is greater than 0 plus 7. So after relaxation we will get 7 here. As this t and y values are updated via s, so for t, pi value is s, we'll add a path from s to t, and for y, pi value is s. Pi means predecessor, from which vertex we are reaching to this vertex. So with t, x, y and z are adjacent, t to x cost was infinite, now it will be 6 plus 5. 6 plus 5 is 11. Then z cost was infinite. Now it will be 6 minus 4. 6 minus 4 is 2. Next y cost was 7. Now it will be 6 plus 8. It's 14. Is 7 greater than 14? No. So there will be no updation for y. Next check adjacent to y. Adjacent to y are z and x. So 7 plus 9 it will be 16. It's already 2. So no updation. Then 7 minus 3. Previously it was 11. Now 7 minus 3. 7 minus 3 will be 4. So is 11 greater than 4? Yes. So this value will update to 4. And it is updated from y. So we'll delete this path and we'll add a path from y to x. This x value is updated via y. So there is a path from y to x. This z value is updated via t. So there is a path from t to z. Now again try to relax each edges. From x there is a s to t. Previously t cost was 6. Now it will be 4 minus 2. 4 minus 2 is 2. Is 6 greater than 2? Yes. So this t cost will update to 2. In previous step, for t predecessor was s. Now for t predecessor is x. From x by minus 2, t cost is 2. So that's how we add a path from x to t and we remove this path. Now after this t value 2, 2 minus 4, this will be minus 2. Previously it was 2, now 2 minus 4. 2 is greater than minus 2. So that's why this z value will update. Then minus 2 plus 7, it will be 5. 4 is less. We already relaxed each edge for every vertices. Now step 2, 3, 4 is done. Next is check step 5, 6. So is this 2 greater than 4 minus 2? No. Is this 4 greater than 7 minus 3? No. Is this minus 2 greater than 2 minus 4? No. So check for all edges. There will be no updation. These are the final cost. So it will exit from this for loop and it will return true. So S to Y cost is 7. S to Y, then Y to X cost is 4. Then S to Y, Y to X, X to T cost is 2. Then S to Y, Y to X, X to T, T to Z cost is minus 2. Now suppose we want to run Dijkstra single source shortest path algorithm on this graph, then what will be result? So first we'll update t and y as these are adjacent to s. So this value will be 6 and this will be 7. Minimum is 6, so we'll add a path from s to t. Next via t we'll update x value, it will be 11, 6 plus 5. This z value will be 6 minus 4, 2. Now from 11, 2 and 7, 2 is the minimum, so we'll add a path from T to Z. Now Z is reachable, so we'll relax all the adjacent of Z. Z adjacent is X, previously it was 11, now it will be 9. 2 plus 7, it will be 9. Now from 7 and 9, 7 is the smallest, so we'll add a path from S to Y. Next, relax all the vertices which are adjacent to y. Adjacent to y is x and z. Z value is already 2. X value is 9. Now it will be 7 minus 3. It will be 4. So just one vertex is left. We'll add a path from y to x. Now just mark by Dijkstra single source shortest path algorithm. Here shortest path cost from S to T is 6. Whereas in Bellman-Ford, the shortest path cost from S to T is 2. Even this Z value is 2, whereas in Bellman-Ford this Z value is minus 2. We are getting more shortest path in Bellman-Ford. And in Dijkstra, once we add a path from source to any vertex, that will not change. So here there is a path from S to T, but in next step we update this path. We add a path from X to T, but that we cannot do in Dijkstra single source shortest path algorithm. Once we find one vertex cost is minimum, we'll add a path and that we cannot update. So if once you are taking one decision, you cannot reverse that. You cannot go back and you cannot modify that. So that's why Dijkstra algorithm is a greedy technique and Bellman-Ford algorithm is a dynamic programming. We can update the cost repeatedly. And for number of vertices minus one time, we can relax. So by Digestra, we are getting this graph as a single source shortest path, whereas by Bellman-Ford, we are getting this graph as a single source shortest path. The costs are more less than Digestra. So Bellman-Ford algorithm giving more shorter path than Digestra algorithm if negative words are present. And for Bellman-Ford algorithm, running time is order of VE, whereas for Digestra algorithm, running time is order of E log V. This V is more than log V. So for Bellman-Ford, time complexity is more than Digestra algorithm. In Bellman-Ford, running time is order of VE. Suppose number of edges equals to number of vertices, then running time will be order of V square. Suppose number of edges equals to number of vertices square, then running time will be order of VQ. In case of complete graph, number of edges equals to number of vertices square. So if complete graph is given, then running time will be order of VQ. Suppose number of vertices equals to n, then running time will be order of NQ. So the Bellman-Ford algorithm running time depends on number of vertices and number of edges. In today's lecture, I discussed Bellman-Ford algorithm with one example. In next lecture, I will discuss all pair shortest path. If this lecture is helpful for you, please like, share and subscribe. Thank you.